Hey guys, thank you very much for joining tonight's story. Close your eyes for a moment and imagine this a vast dark sky, more stars than you could ever count, stretching endlessly in every direction. Somewhere out there, invisible and silent, waits a trap so perfect that even light, the fastest thing we know, cannot escape once it steps too close. That's a black hole. Their centers, called singularities, are places where the rules of physics twist into a puzzle we still can't quite solve. I bet you won't survive more than 1 minute if you try to visit one. But lucky for you, we're only visiting in imagination where it's perfectly safe. Support us by liking this video and subscribing so we can keep bringing you calm, comforting stories every night. Now close your eyes, listen closely, and let this gentle story ease you into a peaceful slumber. As we travel together tonight, feel free to share, even if just in your mind, how you're feeling right now. Maybe tired, maybe a little anxious, maybe replaying tomorrow's to-do list. Black holes might sound scary, but in the stillness of this story, they become a place to set worries down, to float free of them like dust in starlight. Maybe pull a blanket a little tighter around you. Listen to the quiet sounds of your room and prepare to drift peacefully into our tale. The journey begins long before black holes earned their terrifying reputation. People once looked at the stars and believed they were God's lanterns or even holes punched into a celestial dome. The night sky has always been a place where humans project their biggest fears and boldest dreams. And in a way, black holes are the ultimate dream-fear hybrid. They are invisible predators, yes, but also gateways into deeper questions about what reality actually is. Now picture a star, not just any star, but one far larger than our sun. Its heart burns furiously, forging heavier and heavier elements, hydrogen into helium, helium into carbon, and onward a cosmic kitchen, making the building blocks of life. But even stars, those symbols of eternity in poetry, eventually exhaust their fuel. When the delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity tips, gravity wins. And gravity, as history shows us, always wins in the end. This truth was hinted at as early as the 18th century, when Jean Michel and Pierre-Simon Laplace speculated about dark stars, objects so massive that light could not escape their pull. They had no idea they were brushing against a concept that would terrify and fascinate future generations. Imagine being an 18th century scholar, scribbling by candlelight, proposing that nature might hide monsters invisible to the eye. That's the kind of late-night idea that makes you wonder if maybe they drank too much wine before writing it down. Centuries later, Einstein's theory of general relativity sharpened that wild hunch into precise mathematics. His equations whispered of regions where space-time bends infinitely inward, where the math doesn't just get tricky, it breaks. Still, even Einstein doubted such things could exist physically. The man could rewrite gravity itself, but had the same kind of gut reaction you might nature wouldn't really make something that weird. Scientists are still debating that, or at least the exact flavor of weird these singularities come in. Fast forward to modern astrophysics, and the idea of a singularity becomes unavoidable. Imagine all the mass of a massive star collapsing into a point with no volume, a density so intense that the concept of density stops making sense. It's like trying to describe how many clowns you could pack into a car after you've already removed the car itself. The word singularity is just a placeholder, a signpost saying, physics ends here. Beyond it, we don't yet have the language or equations to follow. Yet black holes don't just gulp down matter. They reshape their neighborhoods. Stars orbit them. Gas swirls around them, heating until it glows. Entire galaxies seem to organize themselves around supermassive black holes sitting quietly at their centers. These are not just cosmic garbage disposals. They are cosmic architects drawing patterns on a scale too grand for us to fully comprehend. At the same time, they capture our imagination for stranger reasons. Fringe thinkers whisper about black holes as portals, as hidden doors, even as seeds of brand new universes. Who wouldn't be tempted by the idea that falling into a black hole might not mean destruction, but rebirth? Granted, you'd be stretched like spaghetti before you got to that rebirth. But hey, no theory is perfect. One quirky historical tidbit: when the term black hole was first introduced by physicist John Wheeler in 1967, it scandalized some audiences. To a polite academic crowd, it sounded a little risque. Before then, people tried calling them frozen stars or gravitationally completely collapsed objects, which sounds about as thrilling as a tax form. Wheeler's phrase stuck because, well, who can resist the drama of a black hole? And so, as we drift into this story, remember, black holes are not just destroyers. They are reminders that the universe is wilder and more imaginative than anything humans could dream up. They bend time, defy light, and leave even the sharpest physicists scratching their heads. And maybe, just maybe as you drift towards sleep, they'll whisper to you that it's okay not to have all the answers. After all, even the universe itself keeps secrets. Gravity, the quiet sculptor of the universe, is the force that makes black holes possible. Everyone feels it in everyday life, the gentle tug that keeps your feet on the ground, the reason apples fall, the excuse you give for dropping your phone on your face while scrolling in bed. But gravity isn't just a household inconvenience. Out in the cosmos, it is relentless, powerful beyond measure, and in the case of stars, it is both their creator and their executioner. A star begins its life in a vast cold cloud of gas and dust. Slowly, gravity gathers this material together, squeezing until the pressure at the core becomes so high that hydrogen atoms fuse, releasing energy in a blazing reaction. That's what lights the night sky, what warms Earth, what powers every flower, every thought, every ice cream cone you've ever eaten. But gravity never stops pulling inward. The only thing holding it off is the energy of fusion pushing outward. Imagine a lifelong arm wrestle, gravity versus fusion. For millions or billions of years, fusion holds its own. Eventually, though, fusion tires out. Gravity never does. When a massive star, say 20 or 30 times the mass of the sun, runs out of fuel, the arm wrestle ends. With no more outward pressure to resist, gravity wins instantly, crushing the star's core inward. The outer layers explode in a supernova, an event so bright it can outshine an entire galaxy for a short time. Fun fact, Chinese astronomers recorded one of these explosions in 1054, and today we still see its aftermath in the sky, the Crab Nebula, a glowing cloud of gas and dust. Imagine being a medieval stargazer, noting a guest star in your scrolls, never realizing you just watched the death of a giant. In some cases, the collapsed core stabilizes into a neutron star, a ball of neutrons so dense that a teaspoon of it weighs more than Mount Everest. That's already ridiculous. But if the star was massive enough, even that neutron star can't resist gravity's pull. There is no force left in nature to hold back the collapse. Everything crushes down into something smaller and smaller until, at least in theory, the core shrinks to a singularity, a point with no size yet all the mass. The ultimate victory of gravity. Scientists are still debating exactly what happens in those final moments. Do the laws of physics really allow matter to become infinitely dense? Or does some new undiscovered law of nature kick in to stop the collapse? String theory, quantum gravity, and other frontier ideas all suggest different endings, like writers pitching alternate finales for the same cosmic drama. Until we can peek inside a black hole and spoiler alert, we'll never know which ending the universe actually chose. But for us dreamers tonight, the picture is clear enough. A dying star collapses, and in its death, it creates one of the most terrifying yet beautiful objects in existence. A black hole is born. Now here's a quirky twist. Stars aren't the only route to black holes. Some scientists suggest that in the early universe, right after the Big Bang, small black holes might have formed directly from the hot, dense soup of particles. These primordial black holes could be scattered across the cosmos right now. Some tiny, some huge, all invisible, unless they happen to gobble something nearby. Imagine billions of mini black holes floating like cosmic landmines, silent and unseen. Not exactly the best bedtime comfort, but hey, space doesn't exist to make us feel cozy. And yet there's a sort of comfort here if you think about it differently. Gravity is the most patient artist. It builds stars, planets, moons, galaxies. It takes billions of years, never in a hurry like a potter working clay across eternity. When it sculpts a black hole, it isn't being cruel. It's simply following its own quiet rhythm. The star's collapse isn't destruction. It's transformation. The matter that once shone as light now bends space-time itself, creating a new kind of object, one that challenges our understanding of reality. Picture yourself floating in space, watching this collapse unfold. At first, the star shines brightly, pulsing with energy. Then it wavers, flickers, and suddenly boom. The outer layers burst outward in a supernova, painting the cosmos with color and light. For a moment, it's dazzling, almost celebratory, like fireworks at the end of the star's long life. But at the center, the core vanishes inward, collapsing so fast you can barely follow. Within seconds, what remains is a black hole, invisible but unmistakable. In its effect, nearby stars shift in their orbits. Light bends around the darkness, gas spirals in heating, until it glows with ferocious energy. You can't see the black hole itself, but you know it's there, like spotting the outline of an invisible beast, by the way the grass bends under its paws. And here's the funnier side of this cosmic death spiral. If aliens somewhere out there have TV broadcasts like we do, maybe they sit down with popcorn to watch exploding stars as their version of must-see programming. Coming up next, another season. Finale this time, it's Betelgeuse collapsing. It's silly, of course, but it helps remind us that even the grandest cosmic events are part of the ongoing show. The universe puts on night after night, so gravity grips, stars collapse, and black holes emerge. The cycle continues across billions of years, again and again, each black hole a reminder of the unstoppable power woven into the fabric of reality. We tiny beings curled under blankets tonight get to tell stories about it, to imagine the unimaginable, and to feel small in a way that's strangely soothing. Because if gravity can handle stars and galaxies, maybe it can handle our little worries too. The moment a black hole is born, it immediately sets boundaries around itself. Boundaries that make the difference between safe and gone forever. That invisible perimeter is called the event horizon. Imagine it as a one-way curtain. Once anything passes through, no matter how fast it moves or how desperate it is to escape, it can never return. Not even light, which zips around the cosmos at nearly 300,000 kilometers per second, stands a chance. That's why black holes appear so perfectly dark, a patch of nothingness, outlined only by the chaos that surrounds them. From the outside, the event horizon doesn't look like a wall. If you were floating nearby, hopefully in a very sturdy imaginary spaceship, it would seem like just another point in space. No glowing border, no warning signs, no cosmic lifeguard blowing a whistle. Cross it though, and your fate is sealed. the laws of physics, at least as we currently understand them, will never let you back out. Scientists often compare the event horizon to the edge of a waterfall. Imagine a river flowing smoothly. A leaf drifts peacefully downstream, maybe pausing near a rock. As it nears the lip of a huge waterfall, the current strengthens. The leaf can still try to paddle away if it had, say, little cartoon arms. But once it tips over the edge, nothing can fight the plunge. That edge is the event horizon, and the black hole is the waterfall no one escapes. Historically, this point of no return idea became more concrete in the early 20th century, when Karl Schwarzschild, serving as a soldier during World War I, used Einstein's new equations of general relativity to describe the space-time around such a collapsed star. It's a strange thought between artillery barrages, a German physicist scribbling equations that would one day define the shape of black holes. His solution revealed a radius around the object where escape became impossible. Today we call it the Schwarzschild radius, and it's basically the event horizon's mathematical fingerprint. One quirky tidbit: if you shrank the Earth down to the size of a marble, its Schwarzschild radius, that is the point where it would become a black hole, would be less than a centimeter. The sun would need to collapse down to about 3 kilometers wide. Makes you feel grateful that stars don't usually go around collapsing for fun. Here's where it gets even stranger from the perspective of someone falling into a black hole. Crossing the event horizon feels oddly uneventful. You wouldn't see fireworks, hear alarms, or feel a bump. It would just be another step, another drift forward. But from the perspective of an outside observer, someone watching you fall, it would look like you were slowing down, freezing in place, right at the edge. Time itself stretches so severely near the event horizon that to them, you'd never quite make it through. You'd fade, dimming slowly until you disappeared, almost like an old TV shutting off. Scientists are still debating whether this is the whole story. Does the infalling person really pass through unharmed, at least until closer to the singularity? Or do exotic quantum effects, the so-called firewalls, burn them to ash at the boundary itself? More on that later, but for now, let's just say physics hasn't sent us a final memo on the details. Think about the emotional side of this for a moment. The event horizon is in some ways the ultimate metaphor for life's irreversible choices. We all have moments where we cross a line knowingly or not, and there's no going back. You eat the entire tub of ice cream you hit reply all by accident. You binge watch an entire season when you promised yourself just one episode. Once the step is taken, the universe doesn't offer a rewind button. The event horizon is nature's version of too late, yet in its silence and invisibility, the event horizon is also a strangely comforting thought. It is not chaos, it is order. Every black hole, no matter its size, obeys the same rules. Whether a stellar mass black hole only a few kilometers wide, or a supermassive one millions of times larger, sitting in a galactic center, the event horizon is always proportional, always precise. The universe might be wild, but it is also consistent. Picture yourself drifting closer. You see a bright disk of gas swirling around the black hole, glowing like a cosmic halo. Jets of energy shoot out from the poles, blasting matter at nearly the speed of light. The black hole itself remains invisible, but that dark sphere, perfectly circular against the glowing whirlpool, marks the horizon. Cross it, and the story continues inside. Stay outside, and you remain a witness to the spectacle. Either way, the curtain is drawn, the rules are set, and here's a light-hearted image to leave you with before you drift deeper into the tale. If Earth ever built a space theme park, you just know there'd be a ride called the Event Horizon. Maybe it's a roller coaster that climbs, slowly edges over the top, then plunges straight down into darkness. No refunds, no turning back. Perfectly on brand. Einstein's general relativity is often described as the greatest love letter ever written to gravity. Instead of treating it as an invisible tug between objects, Einstein painted gravity as the very bending of space and time. Imagine the universe as a giant trampoline. Place a bowling ball on it, the fabric stretches, and smaller marbles roll toward the heavy ball, not because the ball pulls, but because the surface itself dips inward. That's the stage on which black holes play their shadowy game. When Einstein published his equations in 1915, they were dazzling, but intimidating. They suggested that space-time itself could curve so extremely that it might wrap in on itself. The equations whispered that if enough mass collapsed, the geometry of space would funnel down infinitely, creating a singularity. Yet Einstein himself wasn't convinced nature would be so reckless. He famously dismissed some of these extreme solutions as mathematical curiosities, not actual blueprints for the universe. It's like writing a recipe that ends with Step 6, bake until infinity. Tasty, in theory, nonsense in practice, or so he thought. Then came Karl Schwarzschild out on the front lines of World War I. Amid mud, cold, and chaos, he solved Einstein's equations for the case of a perfectly spherical mass. His math showed that if an object collapsed within a certain radius, the so-called Schwarzschild radius escape would be impossible. This was the first theoretical description of a black hole, even if the term didn't exist yet. One historical irony, Schwarzschild died only months later from illness, never knowing how famous his solution would become. It's one of those tragic reminders that history sometimes saves the credit for later generations. Einstein wasn't alone in his skepticism. For decades, many scientists doubted these objects could exist. The singularity, after all, seemed too absurd. Infinity isn't a comfortable word in physics. It's more like a red flag that says, we've hit the edge of the map. Scientists are still debating whether singularities truly exist in the universe, or if our current theories simply break down under such extreme conditions. Here's a quirky tidbit for you. The first time anyone mentioned singularities in a pop culture setting was in pulp science fiction magazines during the mid-20th century. Writers loved tossing around words like singularity and hyperspace, often with very little idea what they meant. But the mystique stuck. By the 1960s, singularities weren't just theoretical puzzles. They were becoming the villains and gateways of sci-fi stories everywhere. Back in the academic world, Einstein's equations hinted at other strange possibilities too. In 1935, with Nathan Rosen, Einstein proposed what we now call a wormhole, a bridge connecting 2 points in space-time. The math suggested such tunnels might exist, though fragile and short-lived. Imagine him reluctantly acknowledging yes. Technically, the math allows for it, but please nobody start building interstellar highways just yet. Of course, science fiction did exactly that, fueling decades of imagination. Meanwhile, real evidence piled up. Astrophysicists noticed stars orbiting invisible companions, X-ray sources with no visible star, and galaxies glowing from furious activity at their centers. Each clue whispered Einstein's equations weren't just math tricks, they described real monsters lurking in the cosmos. And every time a new observation matched his predictions, those equations seemed less like speculation and more like prophecy. For a sleepy night perspective, picture the equations themselves as quiet scribbles on paper, neat little symbols and lines. And yet hidden in those curves of ink is the fate of stars, the birth of black holes, and the bending of time. How wild is it that something so enormous and terrifying can be foretold by a few symbols that fit on a chalkboard? It's like sketching a stick figure and accidentally predicting the next extinction-level event. Now imagine yourself as Einstein pacing around your study here, already chaotic enough to suggest he wrestled with space-time itself. He might have muttered, "Surely the universe won't take my equations." That literally, joke's on him. The cosmos took the equations, built the black holes, and sprinkled them everywhere like cosmic confetti. And so relativity doesn't just describe planets orbiting stars. It tells us what happens when the show ends, when the star's curtain falls and gravity insists on an encore. From the neat scribbles of 1915 to the glowing disks around distant galaxies, Einstein's equations remain the backstage pass to understanding black holes. It's a reminder that even the sharpest human minds sometimes hesitate to believe their own discoveries. And maybe, when you're lying in bed tonight, worrying if tomorrow will go as planned, you can remember that Einstein doubted his own math too. If he can question the nature of reality and still give us the most elegant theory of the century, maybe it's okay to leave some of your own uncertainties unresolved for now. The chase to prove black holes exist has all the flavor of a detective story, complete with mysterious suspects, skeptical investigators, and finally, the smoking gun. For decades, black holes were purely theoretical creatures like dragons that scientists whispered about but had never seen. The math was convincing, yes, but convincing math doesn't exactly tuck you in at night. People wanted evidence. The first major clue appeared in the 1960s, when astronomers detected powerful X-rays pouring from a point in the constellation Cygnus the Swan. These X-rays didn't come from the kind of star you could see with your backyard telescope. Instead, they seemed to originate from something invisible, feeding hungrily on a nearby star. This object earned the name Cygnus X1, and it became the first serious black hole candidate. Here's the fun part. When Cygnus X1 was discovered, the famous physicist Stephen Hawking bet his friend Kip Thorne that it wasn't a black hole. Hawking was cautious and maybe a little mischievous. Years later, when evidence piled up beyond doubt, Hawking admitted defeat and mailed Thorne a subscription to Penthouse magazine as payment. Not exactly the scholarly gesture you'd expect, but hey, physicists are people too. As the decades passed, astronomers uncovered more and more candidates. They noticed binary systems where one visible star danced around an invisible partner, moving too fast for the unseen object to be anything but immensely heavy. They also discovered galaxies whose cores blazed with radiation, powered not by stars, but by supermassive black holes devouring gas and dust. One quirky historical note: in the 1970s, scientists coined the term quasar for these bright cores short for quasi-stellar radio sources. At the time, nobody quite understood them. Today, we know they are among the most dramatic signs of black holes in action. Still proving black holes beyond doubt required more than indirect hints. Astronomers began tracking the stars near the center of our own Milky Way. Using powerful telescopes, they mapped the orbits of stars whipping around something invisible at the galaxy's heart. One star in particular, named S2, completed a tight orbit every 16 years around a point that had no visible star, no shining object, just an emptiness packed with the mass of 4 million suns. This invisible anchor is Sagittarius AI, the supermassive black hole at the core of our galaxy. Scientists are still debating the finer details of what's happening right at Sagittarius A. Is the region calm, or is it occasionally erupting with bursts of radiation? But what's not in doubt anymore is that it's there. Gravity itself refuses to lie. Here's a quirky tidbit. When the discovery of Cygnus X1 first made headlines, some newspapers described it as a star eating its companion. That's not technically wrong, but it does sound more like a soap opera plot than a scientific breakthrough. Imagine a star nervously checking the menu while its invisible partner orders the companion special. The history of black hole hunting also reminds us how evidence changes minds. For years, scientists resisted the idea because it seemed too strange. Then one by one, observations stacked up like dominoes until even the most skeptical had to admit the monsters were real. It's a bit like finding out Bigfoot exists, except instead of footprints in the mud, you've got stars whipping around at impossible speeds. The story is ongoing, of course. New telescopes keep sharpening our vision. Space-based observatories like Chandra and Hubble have revealed glowing accretion disks and jets streaming thousands of light years into space. Each image adds another brushstroke to the portrait of these once invisible creatures. And just like detectives solving a case, astronomers piece together the clues patiently until the mystery turns into certainty. For us tonight, tucked into blankets, there's a calming lesson here. Even the biggest cosmic mysteries yield to persistence. Decades of watching, measuring, debating, and sometimes even betting on the outcome eventually pulled black holes out of the shadows of theory and into the light of evidence. And if you're still a little nervous about them, here's a comforting thought. The nearest known black hole is thousands of light years away. You don't need to worry about one sneaking up on Earth while you're sleeping. Unless, of course, primordial mini black holes are zipping around invisibly in the solar system. But scientists are still debating that, so maybe just don't think about it too hard. Imagine floating near a black hole far enough to be safe but close enough to feel its influence. The strangest thing you'd notice isn't the darkness, it's time itself slowing down. Gravity doesn't just bend space, it bends time too. Near a black hole, the stronger the gravity, the slower time ticks, compared to regions farther away. It's like the universe installed a cosmic snooze button, but only for the unlucky ones close to the abyss. This effect isn't just science fiction. It's a prediction of Einstein's relativity, and we've tested it right here on Earth. In the 1970s, scientists put super precise atomic clocks on airplanes and compared them to identical clocks left on the ground. The clocks on the planes tick slightly differently, proving that motion and gravity distort time. In everyday life, the difference is tiny. Your wristwatch doesn't care if you're on a mountain or at sea level. But near a black hole, the effect becomes dramatic, stretching seconds into centuries. Here's where things get eerie. If you watched a friend falling toward a black hole, their movements would slow down as they neared the event horizon. To you, it would seem like they froze in time forever, suspended on the edge. But from their perspective, everything feels normal. They drift inward heartbeat, steady time flowing as usual, until they cross the event horizon, and the outside world is lost forever. Scientists are still debating exactly what happens after that, but the paradox of two people experiencing time so differently is one of the strangest gifts of relativity. One quirky tidbit, this idea of time dilation, inspired scenes in Christopher Nolan's movie Interstellar. Remember the planet near the black hole where every hour equals 7 years on Earth? That's based on real physics. Nolan even consulted physicist Kip Thorne to get it right. Of course, the movie skipped over some messy details like how such a planet might actually get fried by radiation, but the basic idea was solid. Hollywood rarely gives you equations, but in this case, it gave you relativity with popcorn. Time near a black hole isn't just stretched, it's warped in ways that challenge imagination. Light itself bends around the black hole, circling it in tight loops before escaping. If you hovered at a safe distance, you might see bizarre sights the back of your own head, light making a full lap around the hole to meet you from the front. Space and time twisted together turn into a hall of mirrors. Scientists sometimes describe this as gravitational redshift. Light climbing out of a strong gravitational field loses energy, its wavelength stretching into the red end of the spectrum. If you could shine a flashlight upward while standing near a black hole, its beam would crawl away sluggishly, turning redder and redder until it vanished. Even information itself slows down, as if the universe is whispering, "You've gone too far." Think of it this way: gravity near a black hole is like molasses poured over time. Far from it, clocks tick briskly, voices sound crisp, and signals move freely. Close to it, everything drags, stretches, and slows, until moments feel eternal. For someone lying in bed right now, perhaps restless or worried, maybe there's comfort in that thought. The universe itself has places where time takes a deep breath, where seconds linger and hold, refusing to rush forward. Here's a playful joke. If you ever need more time to finish your homework or a deadline, just tell your teacher you'll be working near a black hole. Technically, you'll be correct. You get infinite extensions. The problem, of course, is that your laptop and you wouldn't survive the trip. Minor detail. Back in history, the first people to really wrestle with these effects weren't movie directors, but theoretical physicists. John Wheeler and his colleagues in the mid-20th century popularized the concept of space-time stretching near black holes, coining vivid phrases like black hole and wormhole to make the math sound more alive. Wheeler in particular had a knack for metaphors, turning abstract physics into imagery we still use today. Without him, we might still be calling them frozen stars. And honestly, frozen star dilation doesn't quite roll off the tongue. And so time around black holes isn't just a neat trick. It's a clue that the universe is far stranger than intuition allows. To fall toward one is to step into a zone where minutes and years lose their meaning, where the cosmos itself rearranges the rhythm of existence. It's unsettling, yes, but also a little magical. So as you lie here tonight listening and drifting, think of time not as a straight line, but as a flexible fabric. Sometimes stretched thin, sometimes folded, sometimes gathered tight. The black hole is simply the most dramatic seam in that fabric, a reminder that reality has more ways of being than we're used to. And maybe the thought of slowed down time can ease your own racing clock tonight. Falling toward a black hole isn't like falling toward Earth. Our planet's gravity pulls everything more or less evenly. Sure, if you trip over your cat in the kitchen, gravity makes your forehead meet the floor, but at least all of you goes down together. A black hole, though, it doesn't play fair. Its gravity changes so sharply from one end of your body to the other that it stretches you into something truly ridiculous, long, thin, and hopelessly doomed. Scientists have a fancy name for this tidal forces. Everyone else calls it spaghettification. Picture this: your feet are closer to the black hole than your head. The pull on your feet is stronger, tugging them down faster. Your head lags behind and your whole body elongates like taffy. Your arms stretch outward too, not because the hole wants a hug, but because gravity is weaker sideways than it is lengthwise, so everything squishes inward. You become a noodle, a cosmic linguine dangling helplessly toward the singularity. If that isn't the universe's cruelest pasta joke, I don't know what is. This isn't just speculation. Tidal forces are a real phenomenon we see right here on Earth. The moon pulls on the oceans, creating tides. The side of Earth facing the moon feels a stronger tug than the far side, so water bulges in and out. Same principle, smaller scale. The difference is that instead of gentle waves lapping against the shore, a black hole's tides can tear apart stars. Astronomers have actually seen this. When a star drifts too close to a black hole, telescopes capture the flare of light. As the star is shredded its gas, spiraling inward like whipped cream sucked into a blender. One quirky tidbit: in 2014, scientists observed such a stellar spaghettification in a galaxy 290 million light-years away. The event had a rather bland catalogue name, ASASSN 40 Li, but in the press it was nicknamed the Tidal Disruption Event. Imagine the poor star shining happily for billions of years, only to end up as leftovers in a cosmic spaghetti machine. Not the retirement plan it hoped for. Now here's the funnier side: if you could somehow watch yourself stretching, you might not even realize it at first. From your own perspective, everything would feel normal. Time slows down, signals distort, and the process creeps along. Meanwhile, to an outside observer, you'd look like you were being pulled apart in slow motion, stretched into a noodle, and then vanishing beyond the event horizon. It's like the universe's cruel version of slapstick comedy, stretching, wobbling, then disappearing. Scientists are still debating the exact fate of matter inside the event horizon. Does spaghettification continue all the way to the singularity, or does some new quantum rule intervene, turning matter into something else before it becomes infinitely stretched? Nobody knows. Physics at that depth is like a map that stops mid-sentence marked with a giant "here be noodles." And while the physics is terrifying, the metaphor is oddly comforting. In a way, spaghettification is just another reminder of how gravity demands balance. When forces differ across distance, stretching happens. On Earth, that means gentle tides and waves that soothe beachgoers. Near a black hole, it means destruction, sure, but the rule itself is the same. The universe applies its laws fairly, whether to your evening walk on the shore or to a star drifting into oblivion. Let's sprinkle in a light joke before bedtime. If Italians ever colonize space, black holes are the last place they'll build restaurants. The competition for best pasta would get a little too literal. Historically, scientists first considered the spaghettification problem in the 1970s, when Stephen Hawking and others were teasing out how matter behaves near singularities. The name stuck partly because it's so vivid, and partly because scientists love sneaking food references into serious theories. Without that whimsical label, textbooks might call it differential gravitational elongation, which is accurate, but hardly bedtime material. So here's the picture to hold on to as you drift further into this tale. The black hole doesn't just swallow. It stretches, distorts, and reshapes. It's the cosmic reminder that scale changes everything. The same gravity that keeps oceans on Earth becomes the sculptor of stars, and finally the pasta chef of the universe. As you nestle under your blanket, think of it this way. Yes, spaghettification sounds terrifying, but it's also one of the silliest names ever given to cosmic doom. And if scientists can laugh while describing something so extreme, maybe you can smile tonight at the thought that even the scariest mysteries of space come with a side of humor. Just when black holes seemed like bottomless pits of doom, along came a twist. They aren't entirely black after all. In the 1970s, Stephen Hawking shocked the scientific world by suggesting that black holes can slowly leak energy and eventually evaporate. This strange phenomenon is called Hawking radiation, and it's one of the most mind-bending discoveries in modern physics. Imagine the universe's most terrifying monsters quietly hissing out energy until one day they vanish with a whisper. Here's how it works well, sort of. According to quantum theory, space isn't truly empty. Even in the vacuum of deep space, little pairs of particles pop in and out of existence constantly like cosmic whack-a-mole. Normally, they annihilate each other instantly, leaving no trace. But near a black hole's event horizon, something bizarre can happen. One particle falls in, while the other escapes. To a distant observer, it looks like the black hole is emitting radiation. Over vast stretches of time, This slow leak cost the black hole mass, causing it to shrink. This idea was radical because it blended two giants of physics, quantum mechanics, and general relativity. Hawking showed that even the darkest void must obey the jittery rules of quantum fields. Suddenly, black holes weren't eternal prisons. They were temporary, slowly fading players in the cosmic drama. Here's the quirky tidbit. Hawking himself wasn't thrilled at first. He called his discovery displeasing because it suggested black holes weren't quite as neat and permanent as relativity implied. For years, physicists argued about it, and many still debate the finer points. Does Hawking radiation carry away information? Or is that knowledge destroyed forever inside the hole? Scientists are still debating that, and it remains one of the deepest puzzles in physics. The implications are staggering. If Hawking radiation is real, and evidence strongly suggests it is, then even supermassive black holes will eventually evaporate, though it will take longer than the current age of the universe. Small black holes, however, could vanish more quickly. Primordial black holes, the tiny ones that may have formed after the Big Bang, might already have fizzled away in brilliant bursts of gamma rays. Astronomers still search the skies for those flashes, hoping to catch a black hole's final sigh. Imagine it something that once devoured stars and bent time itself, ending not with a bang, but with a gentle fade dissolving into radiation until nothing remains. It's like a dragon puffing out smoke until it disappears into the breeze. There's something almost poetic about that, the ultimate predators of the cosmos undone by the quiet rules of quantum chance. For a lighter note, picture a black hole on a cosmic diet. Every time a virtual particle escapes, the black hole loses a tiny fraction of its mass. If you think sticking to a calorie plan is tough, try evaporating over trillions of years. Now that's commitment. Historically, Hawking's 1974 paper shook the physics community. It was one of those moments where two fields, quantum theory and relativity, collided in a way no one had expected. His insight even spilled over into pop culture. By the 1980s, Hawking radiation became a phrase you'd hear not just in lecture halls, but in sci-fi novels, TV shows, and the occasional late-night bar argument between grad students. Of course, direct proof is tricky. Hawking radiation is incredibly faint, drowned out by the cosmic microwave background and other noise. Detecting it is like trying to hear a single whisper during a rock concert. Some scientists build analog models in labs using sound waves in supercooled fluids, or light in optical fibers to mimic how horizons might create particle pairs. These experiments can't show Hawking radiation directly, but offer tantalizing hints that the math is right. And yet the debates continue. Some physicists argue that Hawking's picture is incomplete, that subtle details of quantum gravity might change the story. Others think black holes might shrink in unexpected ways, leaving behind tiny relics instead of disappearing entirely. Like many bedtime mysteries, the truth remains just beyond our reach. Still, as you relax tonight, think of the strange comfort in this idea. Even the fiercest monsters fade. Black holes may seem eternal, but in the end they too obey the universe's gentle rule of impermanence. Nothing lasts forever, not stars, not galaxies, not even the darkest holes in space-time. And if the universe's scariest giants eventually let go, maybe we can too. If Hawking radiation shook the world by suggesting black holes slowly fade, the firewall debate lit an even bigger bonfire under physics. The question is this: what really happens when matter crosses the event horizon? Is the fall smooth and uneventful, as relativity predicts, or is there a fiery wall of energy waiting ready to burn anything to oblivion at the threshold? Einstein's general relativity insists on serenity. According to it, crossing the event horizon should feel ordinary. No explosions, no cosmic alarm bells. You wouldn't even notice the moment you passed the line. Only later, as you neared the singularity, would spaghettification take its stretchy toll. Smooth, calm, brutal relativity's version of falling in. Quantum theory, though, throws a wrench in that calm picture. When you consider how information and particles interact at the horizon, something weird happens. To preserve the laws of physics, particularly the rule that information can't simply vanish. Some physicists argue that the event horizon must be surrounded by a blazing firewall of energy. Instead of drifting gently through, you'd be incinerated instantly. No graceful crossing, just cosmic toast. Scientists are still debating that, and oh boy, do they debate it. The firewall paradox, first outlined in 2012, has split the physics community into camps. Some argue that firewalls are unavoidable. Others insist that firewalls are absurd, and that some deeper principle must rescue relativity's smooth horizon. The arguments fill conferences' papers, and probably more than a few awkward coffee breaks among colleagues. One quirky tidbit: when the firewall idea first hit headlines, journalists loved the imagery. Suddenly, you had serious scientists on the evening news describing walls of fire at the edge of black holes. It sounded more like a heavy metal album than a physics seminar, and honestly, if there's ever a band called Event Horizon Firewalls, they already have their first fans lined up. Here's where things get really tangled. From the perspective of an outside observer, information about whatever falls in never truly disappears. It seems smeared across the horizon, encoded somehow in the fabric of space-time itself. To an infalling observer, though that same horizon looks empty and calm. Both can't be true simultaneously, yet both seem demanded by physics. It's like the universe is pulling the ultimate prank. Here have two equally valid but contradictory stories. Sleep well. Historically, this echoes earlier crises in physics. In the early 20th century, scientists faced similar contradictions about light. Was it a wave or a particle? Both awkwardly. The firewall debate may be the modern version of that puzzle, a hint that a new theory, quantum gravity string theory, or something unimagined, will eventually resolve the paradox. Until then, physicists keep scribbling equations, hoping the math reveals which camp has it right. From a bedtime perspective, the firewall paradox is almost reassuring. Think about it. Even the smartest people alive don't agree on what happens when you cross a black hole's border. If you don't have every answer about your own life tonight, you're in excellent company. Einstein, Hawking, and a whole chorus of modern geniuses are still scratching their heads too. Let's add a bit of humor to soften the edges. If black holes do have firewalls, then technically they're the universe's most exclusive bonfires. Too bad marshmallows can't survive the trip. Imagine interstellar camping with the ultimate cosmic s'mores. Whether the horizon is calm or fiery, the debate shows one truth clearly: black holes are more than just massive objects. They are battlegrounds where our best theories clash. Every equation, every thought experiment, every imagined astronaut falling in, they're all part of humanity's attempt to peek behind the ultimate curtain. And so, as you sink deeper into sleep, let your mind rest on this puzzle. Is the black hole a quiet trap, silently swallowing, or a blazing wall burning away the moment you touch it? Either way, the mystery continues, waiting patiently for tomorrow's thinkers to crack it open. For centuries, scientists wondered what truly lies at the heart of a black hole. They knew the gravity must be overwhelming, the density beyond imagination, but the exact picture, that's where things get wild. According to Einstein's equations, everything that falls inside collapses to a single point of infinite density, a singularity. time-space, and matter all crunched into zero volume. It's the ultimate does not compute in physics. Here's the catch. Infinity isn't a real answer. It's more like the universe shrugging and saying, yeah, my math broke. Physicists suspect that singularities aren't actual dots of infinity, but rather signs that our theories are incomplete. The laws of general relativity do a great job explaining stars, galaxies, and even the bending of light, but they buckle under the extreme pressures inside a black hole. Something new has to take over. Quantum mechanics offers clues, though not without headaches. Some physicists suggest that instead of an infinitely dense point matter might condense into a fuzzy quantum structure, where uncertainty blurs the collapse. Others think black holes might harbor something like a Planck star, a super-dense core that resists total collapse thanks to quantum effects. These Planck stars would be unimaginably small, but not infinitely so, offering a neat escape from the infinity problem. Scientists are still debating that possibility, scribbling equations that dance between the rules of gravity and quantum theory. One quirky tidbit: the word singularity wasn't always so cosmic. Historically, mathematicians used it to describe any point where an equation misbehaves. The first time singularity was linked to black holes was in the 1960s, thanks to Roger Penrose, who proved mathematically that collapse into such points is inevitable under general relativity. Since then, singularities have become the most famous do not enter signs in physics. The singularity debate also stirs philosophical questions. If time and space themselves break down inside, what does before or after even mean? Does the singularity erase the past of everything it swallows? Or does that history still exist in some hidden way? The idea leaves even professional physicists staring at the ceiling late at night, much like you might when trying to remember where you left your keys. Relativity paints the singularity as unavoidable, but quantum mechanics resists. It's a standoff between two of the most successful theories ever invented, and neither side wants to blink. This tension has driven decades of research into a unified theory of everything. String theory, loop, quantum gravity, holography. Each one attempts to soften or even erase the singularity, replacing it with something we can actually describe. But none has clinched victory yet. Here's a gentler image to ease into. Think of the singularity not as a monster waiting in the dark, but as a locked treasure chest. We know it's there. We know something is inside, but the key is missing. Every generation of scientists tries a new key, new math, new experiments, new ideas. One day, maybe the lock will click. In the meantime, black holes remind us that even the universe has mysteries it keeps close. We've mapped mountains, oceans, even the surfaces of distant planets. But at the singularity, our knowledge simply stops. It's humbling and oddly peaceful to accept that some corners of existence remain hidden. After all, if everything were solved, there'd be no bedtime stories left to tell. And here's a little joke to tuck you in. If singularities really are just glitches in our equations, then the universe is basically running on buggy software. Someone call cosmic tech support. So as you drift off tonight, let the image of that hidden center settle in your mind. Somewhere out there, light years away, lies a mystery so dense, so unknowable, that even time itself bows to it. It's frightening, yes, but also profoundly beautiful. A reminder that the cosmos still holds secrets waiting patiently for us to dream them open. When people first heard whispers of wormholes, the idea sounded like science fiction sneaking into physics. Yet the math behind them has been sitting quietly in Einstein's equations for nearly a century. A wormhole, in its simplest image, is a tunnel through space-time connecting two distant points. Imagine folding a piece of paper so two dots touch. Poke a pencil through and suddenly the journey between them is instant. That's the dream of wormhole shortcuts across the cosmos. The possibility emerged from Einstein and his collaborator Nathan Rosen in the 1930s. They noticed that the equations for black holes allowed for bridges now called Einstein-Rosen bridges between different regions of space. At first, this was just a curiosity. No one thought they could be real. But over time, the concept grew, inspiring both scientists and storytellers. From Interstellar to old episodes of Star Trek, wormholes became the universe's ultimate express lanes. Here's the catch. Natural wormholes, if they exist at all, might be unstable. They'd snap shut faster than light could cross, like a cosmic mousetrap slamming down. To keep one open, you'd need exotic matter, a substance with negative energy density that resists collapse. Exotic matter isn't your everyday stardust. It's something we've never observed in bulk, though quantum theory hints it could exist in small amounts. Scientists are still debating whether the universe provides enough of this strange stuff to stabilize wormholes. One quirky tidbit: in 1988, a group of physicists, including Kip Thorne, published serious papers about traversable wormholes. Their work wasn't just math for math's sake. It was partly inspired by a request from Carl Sagan, who wanted realistic science for his novel Contact. Thanks to that chain of events, wormholes went from obscure equations to front-row seats in pop culture. Of course, wormholes raise tantalizing possibilities. Could they connect not just distant regions of space but different times? Could you step into one near Earth and emerge near a star thousands of light years away, or even in the distant past? Relativity doesn't forbid it outright, though paradoxes pile up quickly. Time-traveling tourists could make a real mess of history. Imagine someone stepping out of a wormhole to complain that the pyramids aren't tall enough. Still, wormholes remain unconfirmed. We've never observed one never-traced starlight bending in a way that would prove a shortcut exists. Yet the search continues. Some astronomers look for unusual gravitational lensing events, places where light curves as though around a black hole, but with signatures that don't quite match. Others explore whether wormholes might explain mysterious cosmic puzzles, like unusually fast bursts of radiation. The evidence isn't there yet, but the idea lingers too delicious to ignore. For a touch of humor, if wormholes are real, they could completely change interstellar travel. Forget airports, passports, or packing snacks for a 10,000-year voyage. Just step through the nearest cosmic tunnel and hope you don't pop out in the middle of someone else's shower. Historically, wormholes reflect humanity's restless imagination. We've always dreamed of shortcuts, whether through seas, mountains, or space itself. The Silk Road, the Panama Canal, the Internet. Each one was a kind of wormhole shrinking distances in our daily lives. Cosmic wormholes are just the next step in that eternal longing to make the faraway feel close. And there's something soothing in that dream. Even if wormholes never become travel hubs, they remind us that the universe's equations hold room for wonder. The very fact that space-time might allow tunnels and bridges shows how playful reality can be. So tonight, as you lie in bed, picture a wormhole, not as a trap or a danger, but as a hidden door in the universe's house. One that might someday open onto unimaginable horizons. Until then, it waits quietly in the math, like a secret passage we've only begun to explore. The idea that black holes might lead not just somewhere else, but to someone else feels like a bedtime story written by the universe itself. If wormholes are bridges, then black holes could at least, in theory, serve as the doorways. Step into the maw of one, and instead of being crushed, you might tumble through space-time and pop out in another era entirely. Time travel long, the playground of science fiction, slips into the equations of relativity, with a mischievous grin. Einstein's theory doesn't forbid time travel, it just makes it tricky. According to relativity, if you could travel faster than light or cheat by using a wormhole, you could in principle arrive before you left. That opens the door to closed time-like curves loops in space-time, where cause and effect get tangled. It's the cosmic equivalent of writing yourself a letter and then receiving it yesterday. Physicists have played with these ideas for decades. In the 1980s, Kip Thorne and colleagues showed that under the right conditions, a wormhole could act as a time machine. If you accelerated one mouth of the wormhole close to light speed and then brought it back, relativity's time dilation would mean the two mouths age differently. Step into one and you'd emerge in the other at a different point in history. Simple in math, maddening in reality. Here's a quirky tidbit. The grandfather paradox pops up in nearly every discussion. If you go back in time and prevent your grandparents from meeting, do you erase yourself? One physicist jokingly called it the family annihilation problem, though thankfully most bedtime debates about black holes don't go that far. Scientists are still debating whether paradoxes like this would actually forbid time travel, or whether the universe somehow self-consistently avoids them. Stephen Hawking, ever the trickster, once proposed the chronology protection conjecture. In short, the laws of physics conspire to prevent time machines from forming. Maybe wormholes collapse the moment they threaten to create paradoxes. Maybe quantum effects throw up a wall of energy that blocks the loop. Hawking himself hosted a time traveler's party in 2009, sending invitations only after the event. Nobody showed up, which he wryly took as experimental proof that time travel isn't happening, at least not yet. Still, some physicists refuse to rule it out. If exotic matter can keep a wormhole stable, and if relativity's equations hold up at the extreme edges, then black holes might not just be cosmic trash compactors, but portals to elsewhere and elsewhen. It's a lot of ifs, but bedtime is the perfect place for ifs. For a lighter thought, if black holes really do enable time travel, then somewhere out there a version of you from the year 3025 might already be trying to shout at you to buy better socks. The historical fascination with time travel is nothing new. From H.G. Wells's The Time Machine in 1895 to countless TV episodes and comic books, people have been dreaming about bending the river of time for more than a century. What's surprising is that real physics offers loopholes, however slim. It's not all fantasy. The equations leave the door cracked open as though daring us to imagine. But whether or not wormholes become time tunnels, the dream serves a purpose. It reminds us that time isn't as rigid as it feels. Clocks tick, days pass, but relativity whispers that time is woven and stretchy. It can bend slow and maybe just maybe loop back on itself. That idea, wild as it sounds, is already part of our daily lives. GPS satellites literally have to account for time dilation to work properly. Without relativity, your phone's map app would lead you into a river. So as your eyelids grow heavy, picture this a black hole not as an end, but as a mysterious gateway, humming quietly, with the possibility of other times and other selves. Maybe it's fantasy, maybe it's destiny. Either way, it's a reminder that the cosmos is bigger, stranger, and far more playful than our waking hours often allow us to believe. When astronomers captured the first direct image of a black hole in 2019, it felt like humanity had finally peeked into the abyss and seen the monster staring back. The photo released by the Event Horizon Telescope EHT showed a glowing orange ring with a dark center, the shadow of a black hole 55 million light-years away in the galaxy Messier 87. It wasn't just a blurry donut. It was proof that Einstein's predictions had painted the cosmos with startling accuracy. The project was a global effort. The EHT isn't a single telescope, but a network of radio observatories spread across Earth from Hawaii to Antarctica. By linking them together, scientists created a planet-sized virtual telescope capable of resolving the event horizon itself. It took years of planning petabytes of data and algorithms clever enough to stitch together the signals. When the final image appeared on their screens, scientists described the room falling into stunned silence. History had been made. Here's the quirky tidbit: the team's algorithms were so vast that they had to ship hard drives between observatories by airplane. Internet transfers just weren't fast enough. Somewhere in the story of humanity's greatest cosmic snapshot is a humble airline baggage handler unknowingly carrying the data of a lifetime. The image confirmed not just the existence of black holes, but the structure around them. The bright ring wasn't the hole itself, but the superheated gas swirling near the event horizon, glowing like embers before plunging into darkness. The size and shape of the shadow matched general relativity's predictions almost perfectly, a triumph for Einstein's century-old equations. Scientists are still debating the fine details of that ring. Why is one side brighter than the other? Most agree it's due to gas swirling at relativistic speeds. One side beams light toward us, while the other's glow is dragged away. But the exact dynamics of these cosmic whirlpools remain tricky to pin down. Future observations will sharpen the picture, turning that fuzzy orange halo into something crisp enough to watch gas in real time as it vanishes into the void. And the work hasn't stopped. In 2022, the EHT released an image of Sagittarius A, the supermassive black hole at the center of our own Milky Way. Because it's closer but much smaller than M87's giant, the gas around it shifts rapidly, like trying to photograph a puppy sitting still. The result still showed the telltale ring and shadow, proving that our galaxy too has its dark heart. For a lighter joke, when the M87 image was unveiled, memes flooded the internet comparing it to a bagel, a donut, or even the Eye of Sauron. Somewhere, a cosmic bakery is surely missing its most famous pastry. Historically, the quest for a black hole image was long and uncertain. For decades, scientists dreamed of seeing the unseeable, sketching out proposals that seemed impossible with the technology of the time. The success of the EHT proved what collaboration and patience can achieve. Thousands of researchers, engineers, and students contributed, united by a shared desire to glimpse the ultimate shadow. The image also shifted black holes from abstract theory into tangible reality for the public. Before 2019, black holes were imagination fuel, mysterious, invisible, cinematic. After that photo, they became something you could pin to a corkboard or set as your phone wallpaper. Suddenly, the monsters of math had faces, and there's comfort in that, oddly enough. When you see the faint halo of gas glowing at the edge of nothingness, you realize that even the darkest regions of the universe leave traces, signs, and stories. The cosmos doesn't hide its mysteries completely. It lets us glimpse them, pixel by pixel, donut by donut. So as you lie back tonight, remember the image of that glowing ring, a reminder that even when something seems forever hidden, patience and teamwork can bring it into the light. Even the darkest places can leave a glow for us to follow. The moment humanity first heard black holes was just as astonishing as when we first saw them. In 2015, detectors at the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, registered a tiny ripple in space-time. It was the whisper of two black holes colliding over 1 billion light-years away. The signal lasted only a fraction of a second, but it carried the energy of 3 suns converted entirely into gravitational waves. It was like the universe rang a bell, and for the first time, we had ears sensitive enough to hear it. Gravitational waves had been predicted by Einstein back in 1916, but for a century they remained hidden, too faint to detect. Then came LIGO, with its two enormous L-shaped detectors in Louisiana and Washington State. Each arm stretches 4 kilometers lined with lasers and mirrors so precise they can measure changes thousands of times smaller than a proton. That's how sensitive it had to be, because when a gravitational wave passes, it stretches and squeezes space-time itself, altering the distance between those mirrors by a hair's breadth beyond imagination. One quirky tidbit: when the first detection was confirmed, some scientists celebrated with champagne, while others double-checked the data for months to make sure it wasn't a prank by mischievous colleagues. Apparently, practical jokes at LIGO had included hiding rubber ducks in sensitive equipment, so the paranoia wasn't entirely unfounded. But no, it was real. Humanity had gained a new sense. Scientists are still debating what gravitational wave astronomy will ultimately reveal. Already, it has given us a new way of studying black holes, not by their light, which can be faint or hidden, but by the vibrations they send across the universe. Each collision creates a unique signature, a kind of cosmic drumbeat. Some are deep and heavy from massive black holes merging. Others are lighter from neutron stars colliding. With more detectors, we can triangulate their locations, mapping invisible cataclysms like cosmic seismologists. The discovery also sparked humor in the community. Someone described LIGO as the world's most expensive ruler, which is both true and wildly undersells the achievement. That ruler is now measuring the waves of space-time itself, something no tape measure from a hardware store could dream of. Historically, the achievement echoed Galileo's first use of the telescope. Just as Galileo opened a new window with visible light, LIGO opened an entirely new spectrum of astronomy. For centuries, we've relied on light-visible radio X-ray and so on to study the skies. Gravitational waves add a brand new channel, letting us sense the universe's most violent hidden events. Since 2015, dozens of black hole mergers have been detected. The catalogue keeps growing, revealing unexpected things. Some black holes are heavier than we thought possible. Some pairs are strangely mismatched. And in at least one case, a collision may have produced an intermediate mass black hole, the missing link between stellar and supermassive giants. The universe keeps tossing surprises our way as if saying, "Oh, you thought you knew me. Watch this." And here's the bedtime comfort in all this. The fact that we can now hear the universe hum is profoundly soothing. Those faint ripples remind us that everything is connected. When black holes collide in a galaxy a billion light years away, the tremor eventually touches Earth, rocking our tiny planet ever so gently. It's the cosmos whispering, "You're part of the story too." For a little joke before you drift off, imagine if humans had evolved to naturally hear gravitational waves. Every time two black holes merged, you'd be sitting at breakfast and suddenly hear the universe's loudest bass drop. Noise complaints would be complicated. So tonight, picture the universe as a grand concert hall. Stars shine as the lights, galaxies swirl as the dancers and black holes. They provide the percussion beating space-time like a drum. And now, at last, we've learned to listen. For all their power and mystery, black holes also spark one of the strangest debates in physics. What happens to the information that falls inside? In everyday life, information means things like text messages, photos, or embarrassing karaoke videos. But in physics, information means the exact state of particles, the arrangement of matter and energy, the details of how the universe keeps its books. According to quantum mechanics, information can't simply vanish. It must always be preserved no matter what. Black holes, however, appear to break that rule. Toss a planet, or even a star into a black hole, and all the details about it seem to disappear beyond the event horizon. To the outside world, the only things you can ever know about the black hole are its mass, its spin, and its electric charge. This is called the no-hair theorem, which cheekily suggests black holes are bald. They don't keep track of the messy details of what they've eaten. Stephen Hawking made this paradox famous in the 1970s. If Hawking radiation is real, black holes slowly evaporate over time. But when they finally vanish, where does the information go? If it's gone forever, quantum mechanics is broken. If it somehow escapes, we need a new mechanism to explain how. Scientists are still debating that, and it has led to decades of heated arguments, bold theories, and the occasional playful bet. Here's a quirky tidbit. In 1997, Hawking bet fellow physicist John Preskill that information really does vanish in black holes. Years later, Hawking admitted he'd been wrong and presented Preskill with an encyclopedia symbolizing the return of lost information. Physicists do love dramatic gifts when conceding bets. One leading idea is the holographic principle. It suggests that everything inside a black hole might actually be encoded on its surface, much like a hologram. From this perspective, the three-dimensional reality inside is just a projection of data written on the two-dimensional horizon. It's a wild concept, but it neatly preserves quantum rules. Think of it like cosmic bookkeeping. Nothing is lost. It's just written down in a format you don't understand yet. Another contender is the concept of soft hair. In 2016, Hawking and colleagues proposed that black holes do keep some subtle traces of what falls in tiny quantum imprints smeared around the horizon. Not hair in the usual sense, no cosmic wigs, but enough fuzz to store information. Whether that's the whole answer, or just part of it, nobody knows. Historically, the information paradox has driven some of the biggest leaps in theoretical physics. It nudged researchers toward string theory, toward new models of quantum gravity, and even toward the holographic view of the universe itself. In a way, black holes have forced us to rethink not just themselves, but the very foundations of reality. For a touch of humor, imagine if you really could drop your embarrassing high school diary into a black hole, only to have some alien physicist billions of years later reconstruct every cringy detail from the event horizon. Information never dies. It just waits for the most awkward possible moment to resurface. From a bedtime perspective, there's something soothing here too. The universe, it seems, is a careful archivist. Even when things look lost forever, even when swallowed by darkness, the records remain somewhere somehow. Nothing you are, nothing you've done, vanishes without a trace. So as you settle deeper under your blanket, think of black holes not just as destroyers, but as keepers of secrets. Silent vaults, where the story of everything that falls in is stored waiting for the day when physics finally cracks the code. Until then, the paradox remains. Do black holes erase the past? Or do they whisper it back through the quiet shimmer of their horizons? If black holes weren't already bizarre enough, some physicists believe they might be portals to entirely new universes. Picture this: instead of matter being crushed to a dead-end singularity, it rebounds, expanding into a fresh cosmos hidden on the other side. In this scenario, every black hole in our universe could be the seed of another universe, each with its own laws of physics, galaxies, maybe even creatures asking the same bedtime questions we are tonight. The idea isn't pure fantasy. In the 1960s, physicist John Wheeler speculated that what looks like an ending from our side might be a beginning from another perspective. Later models in cosmology suggested that extreme compression could, under certain conditions, bounce rather than collapse infinitely. A singularity might therefore serve as a cosmic womb. One quirky tidbit: some scientists have even joked that our own universe could be the inside of a black hole born in another universe. It sounds outrageous, but mathematically, it isn't impossible. In that view, the Big Bang wasn't the ultimate start, but rather the other side of some unimaginably huge parent black hole. Makes family reunions complicated, doesn't it? Of course, scientists are still debating how plausible this really is. Many argue that without a working theory of quantum gravity, we simply can't know what happens at the core. Others think these bounce models elegantly sidestep the singularity problem by turning collapse into creation. The debate goes in circles, but one thing's clear: black holes force us to think beyond the borders of our universe. Historically, ideas like this fall into the tradition of cosmic pluralism, the belief that many worlds exist beyond our own. Philosophers in ancient Greece once speculated about countless other worlds scattered across the void. Today's physicists echo that same wonder, but with equations instead of poetry. There's also the cosmological natural selection hypothesis, proposed by physicist Lee Smolin in the 1990s. It suggests that universes which produce black holes might be more likely to spawn new universes passing along their physical constants, like a kind of cosmic heredity. In this strange Darwinian picture, universes evolve, and we live in one that happens to be good at making stars and black holes. That's why we're here to ask the question in the first place. For a little humor, if every black hole spawns a new universe, then reality is basically the ultimate nesting doll. Somewhere out there is a Russian grandmother, patiently waiting for someone to finish opening them all. From a bedtime perspective, this idea can be strangely comforting. It means that endings aren't truly endings. A star collapsing into darkness might also be a dawn somewhere else. Every loss, every goodbye in the cosmos could also be a hello in a universe we'll never see. And even if the idea remains speculative, it stirs the imagination. The thought that black holes could be bridges, not tombs, shifts them from pure monsters into cosmic midwives. They may close doors in our universe, but perhaps they open others we can only dream of. So as you sink deeper into rest, let yourself imagine somewhere right now, a new universe may be blooming inside a black hole, its stars just beginning to shine, its galaxies just starting to spiral. And maybe one day a creature there will lie under its own night sky and wonder if black holes are the mothers of worlds. For all the theories and speculations, perhaps the greatest mystery black holes present is the question of unification. Physics today is split between two towering pillars: general relativity, which explains the large-scale structure of space-time and gravity, and quantum mechanics, which governs the tinier scales of particles and forces. Both work brilliantly in their own domains, but they clash violently inside black holes. At the singularity, relativity predicts infinite curvature, while quantum mechanics insists infinities aren't allowed. Something has to give. This tension is why black holes are often described as the ultimate testing ground for a theory of everything. If we can figure out how gravity and quantum physics fit together here, the puzzle might unlock the deepest truths of the universe. It's like trying to merge two competing operating systems into one seamless program. And right now, the bugs keep crashing the code. String theory is one candidate. It proposes that all particles are tiny vibrating strings, and that gravity naturally arises when these strings wiggle in extra dimensions. According to string theorists, the mess at the singularity smooths out no infinities required. But string theory has a reputation problem. It's elegant, mathematical, and hard to test experimentally. Scientists are still debating whether it's the path forward or a beautiful detour. Loop quantum gravity offers another path. Instead of continuous space-time, it imagines space-time as a woven fabric of tiny loops. Under this framework, singularities don't exist. Collapse stops at a finite density. In that case, black holes may bounce, echoing the baby universe idea from before. Yet like string theory, this approach remains mostly theoretical, awaiting evidence. A quirky tidbit Stephen Hawking once joked that trying to unify quantum mechanics and relativity was like trying to marry cats and dogs. They don't play by the same rules, and whenever you think you've got them in the same room, chaos erupts. The quip was funny, but also painfully accurate. Historically, efforts to unify physics date back to Einstein himself. After developing general relativity, he spent decades chasing a unified field theory. He never succeeded, but his determination inspired generations to keep trying. In some sense, black holes are Einstein's unfinished business, daring us to finish the job. Another heated debate surrounds the so-called firewall paradox. Quantum theory says that information must be preserved. Relativity says that crossing the event horizon should feel smooth, with nothing special happening. But if information is encoded at the horizon, then falling in might involve smashing into a wall of high-energy particles, a firewall. If true, it would shatter Einstein's principle that the horizon is locally uneventful. Scientists are still debating whether firewalls exist, or if some deeper principle saves the day. For a touch of humor, if the universe really does have a theory of everything, hopefully, it's written in plain language. Imagine spending centuries to crack the code, only to find it's just a cosmic sticky note reading 42. Bedtime comfort can be found in this uncertainty too. The fact that even the sharpest minds alive can't agree reminds us that not knowing is part of the human experience. It's okay to live with mysteries unsolved, with puzzles incomplete. Sometimes the questions themselves are what give life its wonder. So as you drift, picture black holes as silent guardians of the ultimate secret sitting at the boundary where human knowledge runs out. They're not just destroyers of matter, but keepers of balance, holding the key to reconciling the universe's greatest contradictions. Someday, perhaps, we'll unlock their code. Until then, they remain the perfect bedtime riddle, a whisper of infinity wrapped in the quiet cloak of the night sky. At last, all the strands of black hole mystery draw us toward the final frontier, what truly lies beyond the singularity, if such a thing even exists. The singularity is often described as a point of infinite density, where all known laws of physics collapse. But physicists suspect infinity isn't a real destination. It's a placeholder, a flashing error message telling us our equations have broken down. Something else must be hiding there, some deeper layer of reality not yet revealed. Some propose that singularities don't exist at all. Loop quantum gravity, as we mentioned, paints space-time as a granular fabric. In that picture, collapse halts at a finite density, producing not a tear in the cosmic code, but a bounce perhaps leading to a new universe. Others see the singularity as a doorway to exotic states of matter, where particles melt into pure geometry or quantum foam. Scientists are still debating whether singularities are real places or just mathematical mirages. A quirky tidbit, Roger Penrose, who shared the Nobel Prize in 2020 for his work on black holes, once suggested that singularities might even recycle universes endlessly. In his conformal cyclic cosmology, our Big Bang could have been the far future of another universe. Its death folded into our beginning like cosmic origami. It's the ultimate bedtime loop. There is no first page, only chapters rolling endlessly onward. Historically, singularities were treated as the ultimate stop sign. In the 1930s, Oppenheimer and Snyder modeled a star collapsing into a singularity, and physicists thought, well, that's the end of the road. But Hawking and Penrose in the 1960s proved that singularities weren't just exotic possibilities, they were inevitable under general relativity. That realization pushed the paradox into the heart of physics, daring scientists to resolve it. For humor's sake, imagine if someone finally peers beyond a singularity and finds a cosmic storage closet. Inside all the socks lost in dryers, every vanished left glove, and maybe even the answer key to life's little mysteries. The universe does enjoy hiding things after all. But here, as our long journey winds down, notice the shift. Black holes are no longer just devourers of light or engines of destruction. They've become symbols of possibility, hints of hidden dimensions, new physics, maybe even rebirth. What lies beyond may not be annihilation, but transformation. And in that idea lies the comfort. Just as a black hole transforms matter and energy into something unseen, so too do endings in our own lives open the way for beginnings we cannot yet imagine. The unknown doesn't always mean erasure. Sometimes it means becoming something greater. Now let's let the story soften. The edges of thought blur like starlight seen through half-closed eyes. The roaring engines of collapsing suns quiet into a steady hum, a lullaby carried across space-time. The vast debates of physicists fade to whispers, leaving behind only the gentle truth that mystery itself is a kind of beauty. Imagine yourself floating at the edge of a black hole, not with fear, but with calm. The horizon glows softly, not as a warning, but as a candle in the night. Beyond it lies something unknown, yes, but also something timeless. Something woven into the fabric of the cosmos that also weaves quietly through you. So breathe slower now. Feel the heaviness in your body, the weight that no black hole can rival pressing you gently into your bed. The universe is immense and full of riddles, but here, in this quiet moment, you are part of its story. No need to solve it all tonight. Just rest, carried by the same laws of nature that guide the stars. The mystery of black holes remains and perhaps always will. But that's the wonder. They are not answers to be finished, but questions to dream with. And now, as our tale closes, let's slow everything down. Imagine the night sky above you, stretching wider, its velvet darkness not empty, but filled with quiet presence. The stars blink like distant lanterns, steady and reassuring. Somewhere out there, black holes turn silently, their gravity folding space, their horizons glowing faintly. But here, in this room, in this bed, everything is safe, calm, and still. Let your breath deepen. Inhale gently, hold for a moment, then release slowly. Feel your shoulders loosen, the muscles in your face soften. Each breath is like the universe expanding and contracting a rhythm as old as time itself. Now picture yourself floating not near a black hole, but in the gentle cradle of space, weightless and serene. There is no pull, no rush, no collapse, only the slow drift of starlight around you. Each worry you carry today falls away, shrinking until it vanishes like a pebble tossed into a cosmic sea. Perhaps you wonder what lies beyond all mysteries. Perhaps the thought of singularities and hidden universes lingers in your mind. Let those thoughts drift too, not needing answers, only resting in the knowledge that the universe itself is still wondering. Even the brightest minds can pause, let go, and trust the silence. You can too. The night now holds you softly like gravity that comforts instead of crushes. Your blanket is your event horizon, wrapping you in warmth, guarding you from everything outside. There's no need to travel further. You are already in the quiet center of your own universe. Close your eyes more deeply. Feel the steady beat of your heart, a rhythm echoing the pulse of stars, the hum of galaxies. The cosmos continues its dance, but for you, the only step needed now is rest. So let go. Drift inward. Fade with the night. The universe will wait.